In our previous videos, we learned about the basics of multi-node modeling and how to set up a distribution network with power flow. But that was just the electrical part. Microgrids often have multiple energy flows, including thermal loads such as heating and cooling. By optimizing both electrical and thermal elements, we can increase the cost efficiency of our microgrids. In this video, I'll show you how to set up thermal energy flows and components in Xendee's multinode. Let's revisit our previous airport model. Remember that we had set up a multi-node model with 3 nodes. A feeder node that distributes power through the network, and 2 nodes to represent Terminal 1 and Terminal 2. Additionally, we have some DERs to help with on-site generation and provide backup power. This time, we want to add a district heating and cooling system. This means that the heating and cooling are distributed from a central source. In this case, we'll assume that the central source is also the feeder node. Then, we'll add insulated pipes to enable transport of heating and cooling to our 2 terminals. Let's start by adding our heating and cooling loads. I already have a building load icon on Terminal 1, so I can add my heating and cooling loads under the same icon. Here, I'm directly uploading a water heating profile for this terminal. I'm uploading my data in kilowatt therms, but you can upload heating time interval data files in other thermal units as well. Additionally, I'm directly uploading a space cooling profile for this terminal. These are all the load profiles I need for the Terminal 1 building. I won't show it in this video, but I repeated the exact same process for the Terminal 2 building. Note that you'll also have the option to add other thermal profiles such as space heating and refrigeration, but we won't do that in this video. Now that I've completed adding my thermal load profiles, I need to add DERs that can provide heating and cooling. It's important to make sure that your site has thermal technologies that can meet the thermal demands. Unlike electricity, we can't buy any cooling or heating, and they have to be generated on-site. If there is insufficient capacity for any of our thermal demands, we will get an infeasible optimization result. Let's start with cooling. From the Symbols tab, I'm adding an electric chiller and assigning it to our feeder node. In this case, I already know that I want an electric chiller to meet my cooling demand and its capacity. So I'm setting the technology decision to forced and defining its capacity. However, you can use the Consider option to let Xendee find the capacity for you if you don't already know the capacity. Now let's do the same for the heating demand. From the Symbols bar, I'm adding a boiler and assigning it to the feeder node. It's also a required asset, so I'm setting it as forced and defining its capacity. Similar to cooling, it's important to ensure that the heating capacity is capable of meeting the heating demand. Now that we've added our existing thermal DERs, we need to set up the pipes in the district heating and cooling system so that our 2 terminals can receive the energy. Let's add our cooling pipes first. From the Symbols bar, I'm going to click on the cooling pipe symbol to add a connection between the feeder and Terminal 1. Here, I'm directly entering the capacity and loss coefficient. Note that if your capacity is not large enough to deliver the required energy for the end-use demand, you will get an infeasible solution. However, if you leave these values blank, Xendee will assume infinite capacity and no losses for these pipes. Once I save these, I'm repeating the same cooling pipe process to connect Terminal 2 to the feeder. Now that we've connected the district cooling pipes, let's do the same thing for heating. From the Symbols bar, I'm going to click on the heating pipe symbol to add a connection between the feeder and Terminal 1. Here, I'm directly entering the capacity and loss coefficient. Again, making sure that my values are appropriate for this site. Then, I'm repeating the same cooling pipe process to connect Terminal 2 to the feeder. Now that we've connected our district heating and cooling system, we can run an optimization to see how they work. Like usual, a quick optimization will tell us our optimal DER sizes for any new investments, but let's focus on the thermal energy part of the reporting this time. In the Energy Balance and Technology Investments tab, we now have extra summary pie charts dedicated to our thermal loads. Our heating demand is all being met by the boiler, so all of the balance comes from fuel. Similarly, all of our cooling demand is being met by the electric chiller, so all of the cooling balance comes from electricity. If we have multiple sources of heating and cooling, these charts will break down the different energy sources. In the Balance of Systems tab, the Network Bill of Materials now also includes line items for our heating and cooling pipes. Since I had input the unit costs for these pipes, their total costs will also be reflected in the Bill of Materials. Let's take a look at the dispatch charts. In addition to the electricity dispatch, we now have two separate tabs for the heating and cooling dispatch. We can also look at the dispatch for individual nodes, which enables us to look at the heating and cooling for different locations in the district heating and cooling system. Let's take a look at the heating dispatch at the feeder, where the boiler is located. All of the heat is generated here for the district heating. For example, at hour 0, we see that 1,280 kilowatt therms of heat is produced. This number is the amount of heating that must be produced when accounting for the loss coefficient of our heating pipes. So by the time the heat is transported to Terminal 1 and 2, there is enough heating to serve both heating loads. Now let's switch to Terminal 1's heating dispatch. We see that all of the heat is imported from the feeder node, which is the central source of the district heating system. Similarly, Terminal 2 also gets all of its heating from the feeder. Let's take a look at the cooling dispatch of the feeder, where our electric chiller is located. Similar to heating, all of the cooling is produced here using the electric chiller. At hour 0, the electric chiller generates 5,890 kilowatt therms of cooling, which is the amount of cooling that is required when considering the loss coefficient of our cooling pipes. Finally, let's take a look at our Terminal 1's cooling dispatch. Here, all of the cooling is imported from the feeder, which is the central source of the district cooling system. Similarly, Terminal 2 also gets all of its cooling from the feeder. As we saw, modeling thermal loads in Xendee's multi-node enables us to assign each load to their respective physical locations. With the addition of heating and cooling pipes, this allows us to set up a district heating and cooling system while accounting for losses. We hope that you enjoyed our mini multi-node series, and stay tuned for more Xendee University videos in the future.